Okay, hi everyone. Hello. Okay, hello everyone. First of all, before we start, so just this usual question that whether the PPT is visible to you guys or not, and whether I'm audible or not. In case everything is fine, then we can just like get started. If everything is working fine. Hello, good evening, everyone. I'm good. Good evening. Okay, is everything working fine? Okay, if everything is working properly, then we can just get started. So before I just start, actually we were discussing this insertion in heaps in the last class, right? So I just wanted to ask this, that was there like maybe due to buffering issue, in case you didn't get everything about the insertion process in heaps, then we can just get started with that particular thing again. And then or in case insertion was like very much fine or very much clear to you, then we can just get started with deletion in heaps. But in case you are having any doubt with insertion, we can first discuss about insertion in heaps and then move on to deletion. So you just like let me know in the chat window. Okay, good evening. Oh, is everything working fine? Okay. Okay, so I'll just probably start with insertion in heaps. I'll just start with heaps then. Okay, Nivedita was saying that rotation was not clear. Okay, Nivedita, I'll probably then have to like move over to rotation. In the rotation, like there is just two kind of rotations that are like mainly important. So first one being clockwise and the other one being anti-clockwise. And then we like discussed about the types of unbalanced nodes. So in case you are very much just clear about this thing now, that how do you do clockwise rotation and how do you do anti-clockwise rotation, then you can like very well do other things very easily. I mean, do balance the different types of unbalanced nodes. Like in case of LL, you just have to provide this clockwise rotation. Fine. So in case you are just fine with these two operations, these two basic operations, you can very well do the insertion or deletion in AVL trees. So for the clockwise, this was like very easy. So in case of clockwise, if let's say that this is my tree and I want to like apply clockwise rotation on this particular node, X, A, B, C, D, E, F. So let's say if I want to apply clockwise rotation on this particular node, X, then there are mainly two pointer changes that happen. Actually, if I apply clockwise rotation on this particular node, A will come up and X will go down. So A comes up, X goes down, fine. And the right of this A becomes the left of X. So this is the only change that happens, fine, and rest everything remains the same. So this is what we do in clockwise rotation. So there is only one change is that A will come up and X will go down. Fine, and this is the first thing that you take care of in clockwise rotation. And in the second the second change is that whatever is the right child of A, it becomes the left child of X. So these are like basically the only two changes that happen in the only two pointer changes that happen in case of clockwise rotation. Same is the thing with anti-clockwise rotation. So let's say if I have to apply anti-clockwise rotation here. So let's say if I apply anti-clockwise rotation here. So let's say if I apply anti-clockwise rotation here, then only two changes will occur. First change is that B will come up and X will come down. So B will come up and X will come down, and whatever was the left child of B, it will become the right child of X. Fine, and the rest everything will stay the same. Fine, so this is like this is what happens in case of anti-clockwise rotation. So these are the only two rotations that you need to be like clear with, and in case you are clear with that, you can you'll be like very well easily be able to do the insertion or deletion in AVL Trees. So I'll just get started with heaps insertion, so as to like just build the flow. So in the last class we actually discussed about heaps, as to what heaps are and why do we actually use heap and what are priority queues, and we actually saw this thing that with heaps get max can be done in order of one time, and for min heap get min can be done in order of one time. Fine, so this is like these are the only two changes. I mean, this is the operation that is for which we actually use heaps, and now we were actually discussing about the insertion and the deletion. So in the last class I actually told you this, that in case of insertion we will basically be using percolate up operation. So let's say if I'm having a heap which is, let's say, min heap, so 10, 3, let's say 11, then 13, 14, then 9. So this is one of we can say min heap. So if we have to do insertion in min heap, so let's say I want to insert, let's say 16, or probably I'll just insert 2. Okay, I'll insert 2. Fine, so if we have to insert 2, what do? We simply add 2 to the end of my min heap, and then I start percolating it up. What do I mean by percolating it up? That is to compare my element with its parent. So now 2 will be compared with 13. Now because it is a min heap, so 2 will come up over here and 13 will come up over here. So we basically swap these two nodes. Now 2 will again be compared with its parent. Now because 10 is actually 10 is actually more than 2, so 10 will come down and 2 will come up. Now we will again compare 2 with 1. Now because 2 is actually greater than 1, so we will not percolate this newly inserted node further up. So this is where we stop. So this is how insertion works in heaps. So this is something that we already like discussed, so I just wanted to repeat this. So the main thing now is how do we do deletion in heaps. For deletion in heaps, we basically use percolate down operation. Now what is this percolate down? So I'll just show you that how do we do deletion in heaps. So what actually happens is this thing. So let me like just get rid of this. Okay, So let's say if we are having any heap, let's make max heap this time. Fine. So 10, 8, let's say 6, let's say we are having 5 over here and 2 over here and 4 and 3 over here. Let's say now I want to delete actually this. Now if someone asks you that how will you perform get max in case of min heap, so sorry, in case of max heap, then whatever element is present at the root, you will simply return that. Now actually when I talk of deletion, we are mainly concerned about deletion of the maximum element or removal of the maximum element in case of max heap. They will actually never ask you about this thing that how will you do this particular deletion of like middle nodes. So this particular node, or how do you do the deletion of this particular node, they will generally not ask you, but still the procedure that we are going to discuss can be used for that as well. Fine. So the procedure goes something like this, that if we have to do the deletion of let's say 10 node, then what will I do? I'll simply take whatever is my last node. So this is my last node, right? So I'll simply remove the content of the node that I need to delete, and I will actually add the details of my last node over here. Fine. So the first step is that you remove the data of node to be deleted and add, and in that particular node you add the data of the last node, and you add the data of the last node in that particular position only. So let's say if we were deleting this particular node, you will simply take this particular node's data and you will add it over here. So fine. So now after we are done with this particular step, this is how my max heap is looking like. Fine. But this is actually not abiding by the property of max heap. So what will we do? We will simply do percolate down. So what do I mean by percolate down? In percolate up, I was comparing the element or the node with its parent. Now in this particular case, in case of percolate down, I will actually compare the element or the node with two of its children, this one and this one. Now because 3 is actually less than both of them, right? 3 is actually less than both of them. So you can so what will you do? Because it is actually a max heap, so you would want that whatever is the greatest, whichever is the greater element among these two, that should come up, right? So you would want that 8 should actually come at this particular position. So you will actually swap 8 with 3. So here 8 will come, and in this particular place 3 will come. So this is exactly what I do. I write 8 over here and I write 3 over here. Now again I have to percolate down, and in case of percolate down, what will I do? I will compare this particular element with both of its child, which is 5 and 2. Fine, right? So among 5 and 2, 5 is actually greater, right? So I will swap this, and actually 2 is less than 3, so 3 will never come in over here because it is actually a max heap. So but 3 can go over here, right? So 3 will be swapped with this particular element. So 5 will come in over here and 3 will come in over here. So basically if I have to write down the procedure of percolate down, the procedure will look something like this. So step 2 is to percolate down. So keep percolating it down. So now in some in some vacant space, I'll write down the steps of what do we actually do in percolate down. So in percolate down, you actually compare the node with its two children. Fine. Now if, so the case 1 is if my node is actually, so I am actually taking the case of max heap, so you can accordingly change it for min heap also. So in the node n, or whichever node we were percolating down, so in this case 3 was the node which we were percolating down. So if node n is actually less than any of the two children, because node n will be having two children, right? So if node n is actually less than any of these two children, then you swap node n with the larger children, whichever children is actually large among them. So let's say in this particular case 3 was having 3 node was having 5 and 2 over here, right? So we actually chose 5 to swap with. So this is exactly the case that I am writing over here, that in case my node n is less than any of the two children, then you swap the node n with the smaller, then you swap the node with the larger or the greater child. Fine. And my case 2 is that if my node n is actually greater than both of the children, if my node n is greater than both of the two children, then you stop, then you don't percolate it down further. Simple. Fine. So I hope that this particular procedure is clear. Fine. So if it is clear, then we can just I'll just take a few more examples. So probably I'll now take an example of a min heap. Fine. So I'll just clear this particular space, and I'll keep this particular thing over here only. So now we'll just simply take a min heap this time, and I will try to show you that how do we do deletion in case of min heap. Fine. So I am having a min heap, let's say 1, 4, 2, 6, 8 and 9 over here. Fine. So now this was my min heap. Now I want to delete, let's say if you want to delete this particular node in this case. So in the last case we actually deleted the root node, but in case they ask you, actually in exam they will never ask you to delete this particular node or this particular node or this or this or this. They will always, majorly they will ask you this thing only, that you delete the maximum or the minimum in this case. So because it is a min heap, so they will simply ask you that you delete the min node. But just to show you, or just to make you aware that you can follow the same procedure, so you will, so let's say if I want to simply delete 4, so you will follow this particular first step, that you remove the data of the node to be deleted. So you simply remove it, and then you add this particular data over here. So with this was the last node, right? So you simply add this particular data over here. Fine. And now you start percolating it down. So how do you percolate it down? You compare 8 with 6 and 9. Now because 8 is actually less than one of its children, right? Sorry, because 8 is actually greater than, we are actually having min heap. So simply like you can change the signs accordingly, but over here like I'm not writing the steps for max heap, I mean the min heap also. So if, because 8 is actually greater than one of the two children, so 6 in this case, right? So that is why we will actually now swap the node n with the smaller children, which is 6. So 6 will come over here and 8 will come over here. Fine. So this is how my deletion procedure is complete now. So deletion is actually very easy. So in actually the whole heaps things is very easy. So in heaps, I will simply do percolate up in case of insertion, and in case of deletion I will do percolate down. Percolate down in case of deletion. Fine. So in case you have got this, now we will discuss about the time complexity. As you can see, during the percolate up operation also, we are continuously comparing the node with its parent and with its parent. So at maximum the number of comparisons would be equal to the height of the tree. So the time complexity or the number of comparisons would be equal to the height of tree. Fine. So and the height of tree in case of complete binary tree is always of the order log n. So that is why the percolate up operation only takes order of log n, and hence insertion can be done in order of log n time. And same is actually the case with deletion also, because majorly percolate down can be done at like you'll be percolating it down from the root level to the last level, and the number of levels are always equal to order of log n. So the deletion process will also take only order of log n time in case of heap. Fine. So in case you are having any doubt, you can let me know in the chat window. So I hope if we are like just done with this, then we can move over to the next thing about heaps. So this particular property is actually very important about heaps, this particular property. So I'll just clear this whole slide. This particular property is actually very important and very easy to understand, and there are a couple of questions which have been asked in previous year papers also. So this particular property says that in my min heap, let's take the example of my min heap. So let me just build a min heap. So let's say 10, 20, 15, 16, 18, 22 and 30. So if we are taking the example of min heap, then always my minimum element will be at this level, and my second minimum element will always be at this level. Fine. And my third, this property is not right, and the third minimum element is always found at either second or third level, at either second level or third level. And in case of my fourth minimum element, my fourth minimum element will always be found at third level or fourth level, and my fifth will always be found at either third or fourth or fifth. So at maximum you will have to, like for the fourth minimum element, you will have to check till fourth level only. So fine, you are getting me now, that in case you have to find out the second minimum element, you will actually have to compare only these three nodes only. Fine. So as you can see that the second minimum element in this case is 15, and it is found at this particular level. And if you, in this heap, if you can see that the third minimum is at the level of this. A third minimum is 16, right? And it is at the level 3. So basically the property is this, that in min heap, minimum is always at level 1. The second minimum is always at second level, or it can be at most at second level. So if I have to like term it in a more clear way, I will write it down like this. I will write it down like this. That my second minimum is always at second level, and the third minimum is at most found at third level. कि या तो वो फर्स्ट या सेकंड या हद से हद थर्ड लेवल तक तो मिल ही जाएगा, थर्ड मिनिमम. एंड इन केस ऑफ फोर्थ मिनिमम it can be found at most fourth level. Fourth minimum can be found at most fourth level. Fine. So this particular property is actually like important. And in case of max heap, my second maximum element can be found at most second level, and my third maximum element can be found at most like third level. So this is the property. Fine. So you should take a note of this, because this particular property will come in handy. Sir, Khushbu has written this. Heapifying an array will take order of n actually, Khushbu. So we will discuss about the heapifying process in just a while. And another confusion, Khushbu is saying that second minimum at level 1 na, second minimum, yes. I actually confused this with this. I thought that in whatever discussion that we just had, I just assumed that this is level 1 and this is level 2 and this is level 3. This is what I assumed, in this particular point. Fine. So but this is you can like modify this accordingly, that the second minimum is at most found at this particular level. So within these three elements only my second minimum will lie. So you can like modify this thing, because somewhere in some questions they will like term it as level 1, and in some questions they will term it as level 0. So you can like so the basic funda was, I hope the basic funda was clear, but this is like how you can like modify. So in case I am terming it as level 0, then my statement will be that my second minimum can be found at first level, and my third minimum is at most found at second level, and my fourth minimum is at most found at third level. So in case we are labeling it as this level as level 0, and this level as level 1, and this as level 2. So this is how like we can term it. Fine. So in case this is fine, we can now move over to the heapifying process, that how do we heapify an array. Okay, fine. So what do I actually mean by heapifying an array? So let's say if we are given a simple array of elements that can be 10, 8, 2, 12, 16, 1. So this is my array of elements, right? So in case I visualize it as a complete binary tree, it will look something like this: 8, 2, 12, 16, 1. Fine. So this is how it will look like. Now as you can see that this is neither a min heap nor a max heap. Fine. So how do you actually convert it into, let's say, a min heap? So that particular procedure of converting an array of elements, this particular array of elements into a min heap or a max heap is actually termed as heapifying an array. Fine. Now, how do we actually heapify an array? That is the procedure we are going to discuss. So, heapifying an array can be done. So, you start with first non-leaf node. So, you basically percolate down all the non-leaf nodes. So, the simple procedure says that you percolate down all the non-leaf nodes. Fine. So, what are the non-leaf nodes? So, this is actually a leaf node. This is actually a leaf node. This is actually a leaf node. So, you start off from here and you start percolating them down. So, you first percolate this particular node down, and then you percolate this particular node down, and then you percolate this particular node down. So, you basically, in order to heapify an array, you basically percolate down all the non-leaf nodes. So, if I just go by the procedure, then what will I do? I will first percolate down my second node. Fine. So, how do I percolate down my second node? So, let's say I am actually assuming that I want to convert it to a min heap. Fine. Then if 2 will be compared with both of its children, actually there is only one children right now. So, I will compare it with 1 only. Now, because 2 is actually greater than 1, so I will have to swap. So, 2 will come in over here and 1 will come in over here. Fine. So, now I have percolated 2 down. So, now I need to percolate 8 down. So, how do I percolate 8 down? I will actually compare 8 with these two children. Now, because 8 is actually already less than both of its children, so I need not percolate it down according to the cases that we just discussed, right? And now we actually compare, so actually we percolate this particular node down. So, how do we percolate it down? We actually compare 10 with both of its children. Now, because 10 is actually greater than both of its children, so I need to choose the smaller one because it is actually a min heap. Fine. So, I will swap this particular node with 1. So, 1 will come up over here and 10 will come up over here. And now I need to again percolate 10 down. So, 10 will be compared with 2. So, because 2 is less, so 10 will come in over here and 2 will come in over here. So, now as you can see that my array of elements has been converted to a min heap by simply following this particular procedure. So, this particular procedure is actually like simply one single line, which is actually like not that difficult of a procedure. So, this is how you heapify an array, or this is how you convert an array into a heap. Fine. So, this is how you do this. So, it has been, so we have been able to like able to convert it to a min heap. So, in case of max heap, so let's say if I want to convert it to a max heap, then what will I do? So, I will just show you this. So, let's say that I just wanted to convert this particular array into a max heap. So, I will just repeat the procedure again. Fine. So, this was 10, 8, 2, 12, 16 and 1. Fine. So, I basically need to now convert it to a max heap. So what will I do? I will start with my all the non-leaf nodes. So this particular is my first non-leaf node, so I need to percolate it down, but because 2 is actually greater than 1, so we need not percolate 2 down, because now we are trying to convert it to a max heap. So it is already like in its right position and we will not percolate it down. Now we actually compare 8 with 12 and 16. Now because 8 is actually less than both of its children, so the larger children will actually come up. So 16 will come over here and 8 will come over here. Fine. So 16 comes up and 8 is percolated down. So now 8 cannot be further percolated down, so we actually stop over here. So now we have to percolate 10. We have to percolate down 10. So now we compare 10 with both of its children. Now actually 10 is less than one of its children, which is 16. So 16 will come up and 10 will come down. So 10 comes down over here and 16 comes up. Fine. So I'll probably like make it more clear first. So my 16 came up and this is where my 10 goes. So now I need to, there is a probability that 10 might percolate down further. So I will compare 10 with 12 and 8. Fine. So now because 10 is actually less, okay, so 12 is actually, 10 is actually less than one of its children, which is 12. So I will actually have to percolate 10 further down, and 10 will come down over here and 12 will come over here. So this is how my I have heapified an array. I have converted this array of elements into a max heap. So this is the only simple procedure. So in whole of heaps now, if you will know that how to percolate up and how to percolate down. Fine. So let's in AVL trees we discussed only two basic operations. So the main operations in AVL trees were how to do clockwise rotation and how to do anti-clockwise rotation. Now if you know how to do these two rotations now, then you will actually be very easily able to understand everything in AVL trees. So same is in the case of heaps, that if you know that how to percolate up and how to percolate down, then insertion, deletion, heapifying an array, everything in heaps can be understood in very easier way. Fine. So now discussing about the time complexity of heapifying an array. So actually the time complexity of heapifying an array, as it has been like written over here, generally many will say that the time complexity of this should be order of n log n, but actually the time complexity of heapifying an array is order of n. So right now I am just asking you to just mug this result up, although like I can even prove this, but I don't know whether we have like sufficient time. Okay, so I'll just prove this. Fine, so I'll just prove this. Fine, I'll prove this. So let's just take an example, and with the help of example I'll just try to prove this. So actually heapifying an array takes order of n and not order of n log n. So this is what we are trying to prove. So in heapifying an array, I actually wrote this thing that you start with first non-leaf node and then you percolate it down. So all the nodes at level h minus 1 will be percolated only one step down. Fine. So I am writing these points first and then I will show you the calculations. So all the nodes at level h minus 1 are percolated at most one level down, are percolated down by at most one level. Fine. So in case this particular node is even percolated down, then it will only go down by one level. So now all the nodes at h minus 2 level, by how many levels will they percolate down? By at most 2 levels. Fine. And for all the nodes, so for all the nodes at h minus 2, they will be percolated down by at most 2 levels, and all the node by at level h minus 3, they will be percolated down by at most 3 levels. Fine. And this is exactly what like keeps happening, and all the nodes at the root level, I mean at this level, at level 1. So like you can say it as level 0 or level 1. So like that is all up to us. So like I'll call it probably 0 level. Fine. So they will be percolated down by how much levels they can be percolated down by? H minus 1 level. No, by h level. I mean by at most h level. So this particular thing can be at most percolated down by, I mean in this case it is 2, but in general case if I have to generalize this, then it, all the nodes at level 0 will be percolated down by h. So now if I have to sum this, that how many percolate down operations can happen. So if I sum this all up, so the total time complexity, I'll rather take a variable t. So the total time complexity is actually equal to all the I mean nodes at level h minus 1. How many nodes are there at level h minus 1? 2 raised power h minus 1 nodes. Fine. And they are percolated down by one level. Fine. And all the nodes are at h minus 2 are percolated down by 2 levels. Fine. So this is what happens. So so I am like generalizing it now, and all the nodes at level 0, which is 2 raised power 0, is percolated down by how many levels? By h. Fine. So if I sum all of them up, I will be able to get my time complexity. I hope I was able to convince you till this particular point. Fine. So now we need to basically solve this particular equation. Fine. So I'll just make some space before we just move ahead. Okay, so I have to find out this, the answer to t. Now let's say, what is 2t? If I multiply my left hand side and my right hand side by 2. So I am simply multiplying my left hand side and my right hand side by 2. So multiplying my left hand side and right hand side by 2. Then how will this equation look like? It will look like 2 raised power h plus 2 raised power h minus 1 into 2 plus 2 raised power h minus 2 into 3, and this is how it will go on. And what would be the last term? It would be 2h. Fine, right? Fine. So this is how my 2t will look like. Now if I simply write t also, then what is my t? T is 2 raised power h minus 1 into 1 plus 2 raised power h minus 2 into 2, fine, and plus 2 raised power 2 into h plus 2 raised power 0 into h. So this is my t, right? Now if I subtract 2t minus t, now if I do 2t minus t, that is if I subtract 2 from one equation, then what will I get? This term will cancel out, I mean not cancel out, this will not, where is the pen? Okay, so this will not actually cancel out, this will become this. So this is 2 raised power h and this will become 2 raised power h minus 1, fine, and this will become 2 raised power h minus 2 and so on, plus so this will become 0, so it will keep going till it become 1 plus 0 plus this will remain minus 2 raised power h, fine. So I hope you were able to like get this, that 2h comes over here and 2h minus 1 into 2 minus 2h minus raised power minus 1 into 1, it will give this, and this is how my equation will continue. So now if I sum this up, this is actually equal to n, fine na, because in my complete binary trees, if you take the example of let's say a full binary tree, if you take the example of your full binary tree, then you already know this, that 2 raised power 0 plus 2 raised power 1 plus 2 raised power 2, this is how you find out all the nodes. So this is actually, this whole sum is actually equal to n. Now minus h, minus 2 into h, right? Now what is h? H is nothing but log n. So the whole equation, so t is actually equivalent to n minus 2 into log n. So this can be termed as order of n, fine. So this can be termed as order of n. So basically t is nothing but order of n, and it is actually not order of n log n. So I hope like we were like able to provide a proof as to why heapifying an array takes order of n time and it does not take order of n log n time. So although in paper they won't really ask you a proof, but still I just wanted to discuss with you guys so that it remains in your mind for longer time, fine. So in case you are having any doubt, you can ask me in the chat window, fine. So in case it is clear, we will just move ahead. So this was the this is all that I wanted to discuss about heaps. So now we'll actually simply look at a few questions in heaps before we just move ahead on my linked list part, fine. So now my first question is that what is the minimum number of interchanges that are needed to convert this particular array? So this is the array given and you have to convert it to a max heap. So they are asking that what are the number of interchanges required, fine. So what you do is that you simply like represent this particular array in the form of complete binary tree. And how do you do that? You actually know this, right? 17, 12, 10, 2, 5, 7, 11, 6, 9, 70. So 89, 19, 40, 17, 12, 10, 2, 5, 7, 11, 6, 9, 7. So now basically you have to convert this to a max heap. As you can see that for this particular node, both its children are actually less than 89. So this particular node is actually abiding by the property of max heap. This particular node is also abiding. This particular node is also abiding. This is also abiding. Fine. So this node is also like abiding by the rule of but it is actually abiding by the rule of max heap property, right? So now this is also abiding, but this particular node is actually not abiding by the rule of okay, so we'll simply like I'll not right away check this, so we'll simply follow that particular procedure of how do you heapify an array. So you basically percolate down all the non-leaf nodes. So I'm not really doing this check, so I'm just doing it procedurally, because I can do it in very short form also, but I'll just do it systematically as we just discussed. Fine. So we'll start off with my first non-leaf node and we will try to percolate it down. Fine. So this particular node is not a non-leaf node, this is actually a leaf node. So this particular node is my first non-leaf node. So I will have to percolate it down. So how do I percolate it down? And over here I'll make a variable of number of comparisons or number of swaps that I've made or number of interchanges that I've done. So number of interchanges that I've done. So because in the question this is the thing that they are asking. Fine. So I have to percolate it down. So 10 will be compared with 9 and 70 now, because 10 is actually less than 70 and we are having a look at max heap. So 70 will come up and 10 will come down. So this is how one interchange has happened. So now we can't really percolate down 10 further. So we are done. So in this particular thing we need not percolate 12 down because it is already abiding. This is also abiding. This is now coming over to this particular node. So this particular node is actually, if I compare 40 with 70 and 2, actually 70 is greater than 40. So I will have to move 40 down and 70 up. So 70 will come up over here and 40 will come up over here. So now the number of interchanges have been increased to 2. Fine. So now what we do is, now we compare 40 with 9 and 10. So now as 40 is greater than both 9 and 10, I need not percolate it down further. Interchanges till now is 2. So now I move over to this particular node. This particular node is already abiding by the max heap property, so I need not percolate 19 further down. So now I compare this particular node with both of its children and I just found out that we need not percolate it down further. So I was able to answer this, that the number of interchanges required is only 2. Fine. So now I just hope that you were able to get this particular question also. This particular question was also very easy. Now this is the question. Now this particular question is actually simply using that particular thing, that you have to find out the 7th smallest element. Now if you have to find out the 7th smallest element, then it can be found at most 6th level. If I term my root level as level 0, then it it can be found out at most 6th level. At most 6th level. Fine. So basically I'll have to check 2 raised power 0 plus 2 raised power 1 plus 2 raised power 2 plus 2 raised power 3 plus 2 raised power 4 plus 2 raised power 5 plus 2 raised power 6. So if you these many nodes I'll have to check to find out the 7th smallest element. So what are the total number of nodes that I have checked? It is equals to 2 raised power h plus 1 matlab 6 plus 1 minus 1. That means 2 raised power 7 minus 1, that is equivalent to 127. So basically 127 nodes will be checked before I decide upon that what is the 7th smallest element. So I basically have to check only 127 nodes. Fine. So this is not depending upon the number of nodes in my heap. So my heap can have like thousands of nodes, but finding out the 7th smallest element only requires that I only check till level 6, and I only check the first 127 nodes, and I need not check the other nodes. There might be like thousands or lakhs or any number of nodes. So basically my algorithm for finding out the smallest element is actually not depending upon n, and it will take only order of 127 amount of time, because we have to compare with 127 nodes only, so which is nothing but constant time. Fine. So my answer would be D. Fine. So now we move over to the next question on heap. So my question is that these are the set of elements that are inserted one by one in the given order in a max heap. So they are actually inserted one by one. So let's say that they are inserted, first of all 32 came in, so 32 will of course sit at the topmost position. Then 15 came in. So what do? I simply insert 15 at the end, and then I try to percolate it up. But because 15 is actually less than 32, and in case of max heap, it is already like abiding by the property, so I need not percolate 15 up. So now I will do the insertion of 20. If I do the insertion of 20, I need not percolate 20 up, because 20 is already abiding by the property of max heap. So now I basically insert 30. Now 30 actually needs to be percolated up. Why? Because 30 is actually greater than 15. So 15 will come down over here and 30 will come up over here. Now 30 will not be percolated up further. Why? Because 30 is less than 32. So we simply now insert 12. So how do we insert 12? We simply add 12. We simply add 12 as the last element, and then we try to percolate it up. But there is actually no need to percolate it up, because it is already abiding by the property of max heap. So now we insert 25. So when we insert 25, we actually have to percolate it up, because 25 is actually greater than 20. So 20 will come down and 25 will be present over here. Fine. So this is how my 20 is inserted. So now I insert 16. Now after inserting 16, it need not be percolated up. So this is how my max heap will look like. So this thing is actually very easy, because you know that basically insertion requires percolating up, and percolating it up is not that difficult operation to perform, right? Okay, so in a binary max heap, they are saying in a max heap get max can be done in order of one time. But they are saying that if I have to find out the smallest element, that is I have to perform the operation get min. then how much time will that require? Actually, in order to find out the minimum element, it will always be present at the last level, and the number of elements present at the last level are almost equivalent to n by 2. How? I will just prove this. So let's say if I am having a full binary tree, then at level this there will be 2 raised power 0 nodes, at level this there would be 2 raised power 1 node. So this is how it will like keep continuing, and at last level there would be 2 raised power h node, fine, and at the second last level there would be 2 raised power h minus 1. So if I sum till here, it will come out to be 2 raised power h minus 1, fine, and at the last node, at the last level, I am having 2 raised power h. So this is my number of nodes at last level, and this is the rest of my nodes. So I am terming it as x and I am terming it as y, and we already know that x plus y is equal to n, that my rest of my nodes and the number of nodes at my last level is equal to, I mean if I sum that up, then it would come out to be equal to n, fine. So now what I need to do is I need to find out y, fine. So I just need to find out this thing, and as I can see that x plus y is almost equal, so I can replace my x with y also, right? They are almost equal, I mean there is a difference of only 1, fine. So my y would come out to be almost equal to n by 2. So that is why we can say that I'll only have to search n by 2 number of elements in order to find out the smallest element. So the whole operation of finding out the minimum element in max heap can only be done in order of n time, fine. So I hope I was able to convince you on this, that the number of nodes in the last level is actually equal to n by 2, is almost equal to half of the nodes. So that is why finding the minimum node in the max heap is equal to order of n. Fine. So okay, so if I was able to like convince you on this, then we can now move over to linked list. Now first of all, what are all the types of so linked lists are basically, so I'll not like get much deeper into linked lists, and I'll try to cover linked lists in like a relatively faster manner, because linked lists are very easy, relatively easy to understand, fine. So linked lists are basically, they are not a linear data structure. Linked lists are basically non-linear, they are actually linear data structure, but their storage, they are actually linear data structure only because they are accessed one after the other, but their storage actually is not continuous, fine. So their storage is actually not continuous. So it means that in case of array, because every other element should be continuous. So let's say if my array at element or at index is at address, let's say 100, then my next element or the integer, let's say here I was storing some integer, then my next integer should come at address 104 if this particular integer was taking a size of 4 bytes. So this is actually not the case with linked list, because it doesn't require the continuous allocation of space, and that is actually a good point about linked lists, that they can be stored in a non-continuous manner, and wherever my space is present I can store this linked list node anywhere in the memory. Fine. So there would be less segmentation, so I can utilize that. In case my space is more segmented, then I can even use that space also. Fine. Now coming over to what are the types of linked list. There is singly linked list, doubly linked list, circular linked list, and also doubly circular linked list. So doubly circular linked list is not like that difficult, and in case you would know that what a simple doubly linked list is and what a simple circular linked list is, you would be very easily able to guess this, that what do we do in circular linked list. So now okay, so now we discuss all these types of linked list one by one. So basically we'll be discussing these three main things about linked list. So what first thing being that what is the structure of my linked list node. The second thing being how do I insert a node at the beginning, how do I insert a node at the end, and how do I insert a node in the middle. And the third thing being that how do I do the deletion at the beginning or at the head, and how do I do the deletion of a node in the middle, and how do I do the deletion of a node in the end. Fine. So now first thing first, what is the structure of a singly linked list. So the structure of a node in a singly linked list is, it will simply store the pointer to the next node, and it will store the whatever is the data to be stored in that particular node. So let's say if I am having this node, one node in singly linked list, it will basically have the data part, and this particular pointer stores the address of the next node, or it points to the next node. So this is how the structure of a node looks like in case of a singly linked list. Fine. So now we actually discuss this thing, that how do we do insertion at the beginning in case of singly linked list. So actually this is the main thing to focus over here would be that what is the time complexity of insertions at beginning, at end, and in the middle, and also how many pointer changes will be happening. So basically mainly they would be asking that what is the time complexity of insertion at the beginning. So whenever you are having a linked list now, whenever you are having a linked list, you will always have the pointer to its head. That means you will always have the address of the head stored somewhere in a head variable. So you will always know that wherever my first node is, wherever is the first node of the linked list is. Fine. And we might not know the address of the other nodes. So we can actually find out the address of the other nodes by using the next pointers and then the next pointers. But at the starting, at the beginning, we will simply have the address of only first node. Fine. So now how do we do the insertion at beginning? So if I have to do the insertion at beginning, what will I do? I'll simply allocate some memory to the new node. I will store the relevant data in here, and its next pointer will point to the head. So basically there are only one pointer change that happens. What that is, that my new node's next pointer will store the address of the head node or the first node. and the second thing that happens is that now I will have a new head, that this will become my head. Fine. So my head would now be new node. So there are only two changes that happen. So these two changes can be done in order of 1 and order of 1 time. So basically insertion at beginning in case of singly linked list takes only order of 1 time. Fine. So now we actually will learn that how much time do insertion at end takes. So now yes, so now basically we are having the address of only our head node only, and we are not having the address of other nodes. Fine. So now if we have to do the insertion at the end, that means I need to insert another node at the end like this. Fine. So I want a new node and I want that my last nodes next pointer, okay, I'll not write it over here, I'll write it over here. So my last node next pointer should store the address of my new node. This is exactly what I want, right? But then how do I get the address of my last node? So this is my last node, then but how do I get the address of my last node? So in order to get the address of my last node, I will basically have to traverse my linked list, and traversing my linked list is actually requires order of n time. Fine. So the first step is to traverse the linked list to get the address of my last node. Fine. And whenever you got the address of your last node, you simply have to just make this small pointer change. So this particular step is second step, but this particular step only takes order of 1 time, and this particular step takes order of n time. So all in all, this whole insertion at end happens in order of n. Fine. So now discussing about insertion in the middle. Insertion in the middle also requires order of n time. I'll show you how. Fine. So in case you have any doubt, you can always let me know in the chat window. Okay. So let's say if I have to do insertion at the middle. So let's say if I want to insert a new node in here. So I want that this particular node should be inserted between these two nodes. This particular node should be inserted between these two nodes. Fine. So how do I do that? So basically in order to do this now, I need the address of this particular node. Fine. So it might also happen that I might want to insert the new node over these between these two nodes. Then in that case, I will need the address of this particular node. So how to get the address of this particular node? You simply traverse the linked list, and traversal takes order of n. And after you have got the address of this particular node, so let's say this is node n, then there is only 2 pointer changes that you have to do. What are those 2 pointer changes? that node n's next pointer should now point to my new node, and my new node's next pointer should actually point over to this particular node. So how do I get the address of this particular node? So I could have stored the address of this particular node in here, struct next node, struct node star next node, and next node is equals to node n's next. Fine. So I could have like stored, or I could have like got the address of the next node very easily. So after that, my only 2 pointer changes are required. First one being this, and the second one being that my new node's next should point to my next node. Fine. So this is like these are the only 2 steps that I need to do. This particular step will take order of n, and this particular step will only take order of 1. Also this particular step will take only constant amount of time, and this step will also take constant amount of time, but the step to get the address of my node n will actually require me to traverse the linked list, which will actually take order of n time, which will actually take order of n time. Fine. So this is why insertion in the middle also requires order of n time. So now discussing about deletion at head, middle and end. So in deletion also head can be done in order of 1, but the deletion in the middle and the end will require order of n and order of n time. Fine. So I'll just quickly show you how. So this particular things are relatively like more easier. So in case like you are getting bored, so don't just get bored, because these are like very easier, but just for the sake of completion, I just wanted to discuss this. Fine. So in case you want to do the deletion at the beginning, so I'm not really showing you that how do you do the deletion at the beginning. I'll simply just discuss that how do you do the deletion at the end or deletion in the middle. Fine. So deletion in the middle, if you have to, let's say okay, so you are having the pointer to the head, and let's say you had to delete this particular node. So whichever node has to be deleted, you will always require the address of its previous node. Fine. So whichever node has to be deleted, you will always require the address of its previous node. And how will you get this previous node's address? By traversing the linked list, which will take order of n time. Fine. So getting the previous node's address will actually take order of n time. And after you have got the previous node's address, you can do the deletion in a very easy way. So previous nodes, so there is only one pointer change that happens, that previous node's next pointer will now point to previous node's next. So now it will point over to here. So previous node's next pointer is now equal to previous node's next. Right? So this is the only like pointer change, but this pointer change won't take much time, but mainly the traversing thing will take much more time. And same is the thing for deletion, and if you want to do the deletion at the end, you will require the address of this particular node, and getting the address of this particular node is actually a more time taking task and will require you to traverse the linked list in order of n time. So that is why deletion at the head takes only order of 1, but middle and end takes order of n time. So now I'll just like discuss about all the doubly linked list operations. Okay. So in case of doubly linked list, so first thing that we have to discuss about is that what is the structure of a doubly linked list node. So in case of a doubly linked list, we don't just have the pointer to the next node, but we also have the pointer to the previous node. So this is how my structure of a node will look like. I will basically have the pointer to the previous node, and also my data and the pointer to my next node. Fine. So if I have to discuss about insertion at the beginning, then it will take order of 1, but insertion at the end and insertion in the middle will actually take order of n and order of n time. Fine. And for the deletion also, deletion at the head will only take order of 1 time, and for deletion in the middle and the end, it will take order of n and order of n. So I'll just discuss them as to how will they take order of 1 time or order of n or whatever it is. So first of all, let us discuss the structure of a doubly linked list. So let's say this is how my doubly linked list looks like. So for the head, its previous node pointer will actually be pointing to null, and its next node pointer will be pointing to the next node. And for my 9 node, its previous pointer will point to 10 and the next node pointer will point to 20. And for 20, its previous pointer will point to 9 and its next node pointer will point to null. So this is how like my doubly linked list will look like. Now let's say that if I have to do the insertion at the beginning, then what all things will I do? First of all, I'll allocate some space to my new node and I'll initialize it with the data. Let's say 11 was the data. So there are now only 2 pointer changes that will happen. What are those 2 pointer changes? That my new node's next node pointer, my new node's next node pointer will point to head, fine, and my new node and this particular head, whatever was in my like head, its previous node pointer, which was initially pointing to null, now it should point to my new node. So head's previous node pointer should point to new node. Fine. Now my head will also like change. Head will now not point to this node, it will point to my new node. Fine. So these are the only pointer changes that happen, and all of these pointer changes can be done in order of one time. Fine. So this is how I do the insertion at the beginning. But for the insertion in the middle or insertion at the end, I will actually require, so let's say if I want to do the deletion in between these two nodes, fine, then I will actually require the address of this particular node, and for getting the access or if I want to know the address of this particular node, then I will have to traverse the whole linked list. That will actually require order of n. So that is why insertion at end and insertion at middle actually requires order of n time. I can like show you that what all pointer changes happen, but those pointer changes are actually very easy. So I am actually like expecting that you should know this, but still I'll like show you what all pointer changes happen. So I am probably like just going to show you the pointer changes that happen in case of insertion in the middle. Fine. Okay. Fine. So let's say if I wanted to insert a new node between these two nodes and the data of that node was 11. So there are basically, first of all, I need to get the address of this particular node. So how do I get the address of this particular node? So my step 1 is to traverse the whole linked list. So my first step is to traverse the whole linked list till I find out the address of this particular node. So how do I find out the address of this particular node? By traversing the linked list, and let's say I got the address of this particular node and I am calling it as node n. Fine. The address of this particular node as node n. So now after getting the address of this particular node, what are all the 3-4 pointer changes do I need to do? So the very first pointer change is that my node n's next should now point to my new node, right? So my node n next pointer should actually now point to the new node now. So this is the first pointer change that happened. Now what is the second pointer change? That my new nodes previous should actually point to node n, right? So my new nodes previous should actually now point to node n, and also these two pointer needs to be changed, that for this particular node its previous should point to this and my new nodes next should point to this. So I basically need the address of this particular node also. So before I make all these changes, once I've got the address of node n, I can also get the address of node n plus 1, right? n1 I am calling it. So what if this is the node n1? How do I get the address of node n1? By simply saying this, that node n1 is equals to node n's next node. Fine. So I can get the address of node n1 also. So now if this is the node n1, then the two pointer changes that I need to make is that node n1 previous node pointer, this was next node and this was previous node actually. So because here we have defined it as previous node and next node, right? So that is why I am writing it as previous node and next node. So the two pointer changes are node 1's previous node pointer should now store the address of my new node, and my new node's next pointer should now store the address of my this node n1. Fine. So these are the 4 pointer changes that happen. All these pointer changes will take only constant amount of time, but just getting the address of this node n is actually a time taking task, because we'll have to traverse the whole of the linked list, and this particular step will take order of n time. So that is why insertion in the middle as a whole operation will take order of n time. Fine. So now we'll move over to deletion part, that how do we do deletion in case of doubly linked list. Okay, I'll probably like rub everything. Fine. So for the deletion at the end, it will take only order of 1. For the deletion at the middle, it will take order of n. And for deletion at the end, it will take order of n. Fine. So let me just like draw. So deletion at the head is not that difficult. So I'm probably like just going to show you that what all pointer changes happen for deletion at the middle. So let's say if I want to delete this particular node, then I will have to get the address of this particular node, right? And also I'll have to get the address of this particular node. Fine. So if I have to, so but if I'm having the address of this particular node, then it would be very easy for me to get the address of this particular node. Fine. So basically I need to get the address of this node. And how do I get the address of this node? By traversing the linked list, which will actually take order of n time. Now let's say if I've got this, a node's address stored in previous node del, maybe I've got the address of this stored in previous node del variable or previous node del pointer, then what all pointer changes do I need to make in order to delete this particular node? So the very first thing, and how do I get the address of this particular node? Let's say I'm calling it as next node del. Then how do I get the address of next node del? It would be next node del is equals to previous node del. Its next node will point over here, and then again one more next will point over here. Fine. So this is actually where what next node del will store. How I can get the address of the next node del. So once I've got the address of previous node del, I can easily calculate next node del address also. Fine. So the very first pointer change that I need to do is that previous node's next pointer, it should right away point to my next node del. So that is exactly what I do, that previous node del pointer, its next pointer should point to, so I'll probably rub this. So it should store the address of next node del. Fine. And let's say that what is the next pointer that I need to change? I need to change this, that next node del previous pointer should point over here now. Fine. So next node del pointer, its previous node, its previous pointer should store the address of my previous node del. So once I have made these two changes, I can actually free this particular, I can actually free the memory allocated to this particular node. So these are the only two pointer changes that I need to make. So this can be done in order of 1, but the main thing is that getting the address of the previous node del. This particular step will require us to traverse the linked list, and that can only be done in order of n. Fine. ओके सो हिंदी में I'll try कि मैं हिंदी में भी बात करूँ. ओके तो अब हम so now we will actually like discuss about circular linked list. So first of all, that how the structure of a circular linked list node will look like, and what is the structure of a circular linked list. So there is only one change or one difference between singly linked list and circular linked list. There is only one difference. In case of singly linked list and circular linked list, and that difference is that in case of circular linked list, my last nodes, so in case of singly linked list, this is how my singly linked list looks like. Fine. And my last node's next pointer actually points to null in case of my singly linked list. But in case of my circular linked list, my last node's next pointer will actually point to head. It will actually store the address of my first node. Fine. So this is the only change that is there between my singly linked list and my circular linked list. Apart from this, there is no change between singly linked list and circular linked list. Fine. So in terms of structure also, structure of a node, structure of a linked list node. So in terms of structure of a linked list node, it is same as the structure of a singly linked list node. That is that you are having the pointer to the next node and you are having the data part. Fine. So the structure of the node is also like same in singly linked list and circular linked list, and the only change is that the last node next pointer always points to head. That is the only change. So now discussing about the insertion at beginning, insertion at end, and insertion in the middle. Fine. So now if I have to do the insertion at beginning, in case of circular linked list, it will take order of n time. Why? We'll just discuss. So this is actually a very big thing, because in case of my singly linked list, it was taking only order of 1 time to do the insertion at the beginning, right? But in case of circular linked list, the insertion at the beginning is taking relatively more time. So I'll just show you why. Sorry. Now let's say that I have to do an insertion. Let's say this was my circular linked list, and let's say I had to do the insertion of 0. Now there are basically two pointer changes that I need to do. That is, my new nodes next should point to head. This is the one pointer change that I need to do. And the other pointer change that I need to do is that my last nodes, this is my last node, right? Its next should now no longer point to this particular node, it should now point to this particular node, right? So that is why we say this, that my last node next should now point to my new node. And after I have done this, I can update my head, that my head is equals to new node. So basically this particular pointer change and this particular pointer change are important, but for this particular pointer change I need the address of my last node. And how can I get the address of my last node? By simply traversing only. So getting the address or pointer of the last node basically needs order of n, and these two pointer changes will only take constant amount of time only. Fine. So that is why we say that insertion at the beginning in case of circular linked list will take order of n. Fine. And insertion at the end and insertion at the insertion at the end will also take order of n, and insertion in the middle will also take order of n. Insertion at the end will take order of n time. Yes. So this is how my this is like what is the time complexity in case of circular linked list. Fine. So now I'll just discuss about basic about deletion in case of circular linked list. Deletion at head, middle and end. So I'll not discuss everything, and I'll just because I just want you to give the few basic pointer changes and what is the time complexity of deletion. That is what I want you guys to know, because mainly questions would be framed on the basis of that only. So let's say if I want to do the deletion at head, this is my circular linked list and I want to do the deletion at head. This is my circular linked list. Now if I want to do the deletion at head, basically I'll have to change this pointer also. My last node's next pointer will now be pointing to this particular node. So basically my last node next pointer is changed. Fine. Now how to get my last node pointer? That is possible only by traversing my circular linked list. So that is why deletion at head will take order of n in case of circular linked list. But in case of singly linked list, although it will take only order of 1, but in case of circular linked list, it will take order of n. Now if I have to discuss, and you already know that for middle it will take order of n, and for end also it will take order of n. Fine. So this was the major change that actually happens when compared to circular linked list and singly linked list. Fine. Okay, so this is like the main thing. So we'll now be discussing a few questions on linked list, and then we will. I also like want you to know a bit about doubly circular linked list. So this particular thing is actually very important. Doubly circular linked list. So in case of doubly circular linked list, there are mainly. So I'll just draw the structure. Okay, fine. So basically in my doubly circular linked list, it will be somewhat similar to my doubly linked list only, but there are only two pointer changes. One is that my last node's next pointer will point to head, and the other changes my heads. The other changes that my head's previous pointer, my head's previous pointer will point to the last node. Fine. So these are the only two changes that are there between my doubly linked list and my doubly circular linked list. Now because of this, actually we can reduce the complexity of so many operations. So let's say insertion at the beginning, in case of doubly linked list, will take only doubly circular linked list, I am saying, will take only order of 1. Even the insertion at the end for a doubly circular linked list will take only order of 1. And in case of deletion also, we can have the deletion at the head and the end done within order of 1 time. So I'll just show you that how in case of doubly circular linked list, why we have got the insertion at the beginning and the time complexity of insertion at the end reduced to only order of 1 and order of 1 time only. Fine. So probably like we'll discuss that thing in the next class. Maybe like people are getting bored because this thing is actually relatively more important. The deletion and the insertion in singly linked list, doubly linked list and circular linked list are actually relatively easier to understand, and also like many people do know about this. But for doubly circular linked list, why and I mean this insertion at the beginning and insertion at the end is taking only order of 1 time. We'll discuss this thing in the next class, because probably like some people have left because they were getting bored. So probably we'll discuss about doubly circular linked list in the next class. Fine. So we'll have the next class tomorrow, and I'll meet you guys in the next class tomorrow. Fine. So thank you so much for joining in, and good night. Although like in the end it was getting bored, because I also like know, because the linked list theory part is actually like not that difficult, but if we'll go into the code part now, that how do like what do pointers point to, and how do all those alteration of the pointers do, or if we are like writing the practical code, then it looks very interesting. But right now, because like we are just pursuing the crash course, and I can't really jump into writing the code part, that how do we just traverse the linked list to find out the address of every particular node or previous node. So that is why it is not looking that like interesting, but probably we'll like discuss all the code part in the whenever we are like pursuing the full course part, because in crash course I can't really cover up all the coding part. Fine. So that is why I'll just like leave it up till here, and in the next class I'll discuss about doubly circular linked list and all the questions related to linked list part. Fine, and then we'll quickly move over to stack and queues. Stack and queues won't really take that much time. It can be like done within 1 hour. Fine. So I'll meet you guys tomorrow, and thank you so much.